Hi viewers, welcome back to my class on mechanics of materials. In today's class, I'll explain the secant formula used for eccentric loading of a long column. Now when a long column is centrally loaded, when the load increases, the column buckles. When the column is loaded away from the centroidal axis, that is at a distance e from the centroidal axis, it will induce additional bending stresses in the column apart from the direct stresses induced. This maximum bending stress due to the combined effect of direct stress and additional stress due to eccentric loading can be found out using this secant formula. And secant formula is given as sigma max is equal to P by A into 1 plus EC by K square into sec root of P by EI L by 2. In this, P is the load applied, A is the area of cross section of the column, and EC by K square is known as ratio of eccentricity, where E is the eccentricity, C is the maximum distance to the outermost fiber in the direction of buckling. So if the column is having different dimensions in the x and y directions, which direction the column has least dimension, in that direction column will buckle. So in that direction, what is the maximum distance to the outermost fiber? That is C. Suppose x direction you have minimum distance and y direction you have maximum distance. So in x direction it buckles. So in the direction where the column has least dimension, in that direction column buckles, and in that particular direction what is the maximum distance to the outermost fiber from the centroidal axis? That is C. So C is the maximum distance to the outermost fiber from the neutral axis or centroidal axis, divided by K square. K is the least radius of gyration. And P is the load applied, and E, Young's modulus. I is the moment of inertia of the column cross section. Again, least moment of inertia has to be taken here. L is the effective length of the column, and effective length depends on the end condition, and this secant formula is applicable only for two types of end conditions, one end fixed and other end free, that is this case, and another is both ends hinged. It is not applicable for other types of end conditions because resisting moment induced on the fixed end will prevent this additional buckling when the load is applied with an eccentricity. So it is applicable only for column with one end fixed and other end free, and column with both ends hinged. And this secant formula may be written in a different form. So this is the one which I have shown there in the previous slide, and it can also be arranged where I is AK square. If you replace I as AK square, K square will come out of the root and you will get L by 2K. So you can also write in this form, and also you can write in terms of Euler's buckling load, P by PE. P is pi square EI by L square. When you write it as pi square EI by L square, so when you replace P by pi square EI by L square, you will get once again the same equation. So whichever form is convenient for us, we can use that, and this secant formula gives only the maximum stress induced. So maximum stress will be induced on the concave side of the column. When the column buckles, which direction it buckles, say if it buckles like this, so the maximum stress will be induced on the concave side of the column. The other side tensile stress will be induced. So one side you will have a maximum on the outermost fiber, which direction the column buckles, on the outermost fiber you will have maximum stress induced, and this maximum stress has two parts. One is a direct stress, that is P by A. The other one is P by A into this part, which is the additional stress induced due to eccentric loading. Now let us work out a numerical example. A uniform column consists of 100 mm by 100 mm cross section, which is 2.5 meter long as shown. So it is a column with 100 mm by 100 mm cross section and 2.5 meter long, and is fixed at one end and free at the other end. Using Euler's formula and a factor of safety of 2, determine the allowable centric load for the column and the corresponding normal stress. So using Euler's formula and a factor of safety of 2, determine the allowable centric load for the column and the corresponding normal stress. So Euler's formula you already studied. You can find out the Euler's buckling load, and using a factor of safety of 2, you can find out the allowable centric load when it is load is applied along the centroidal axis. What is the maximum load the column can safely carry by taking a factor of safety of 2, so that you can find out, is already learned. Now second part of the question is, assuming that the allowable load formed in part A is applied at a point 20 mm from the geometrical axis of the column, determine the maximum normal stress in the column, given E is equal to 204 gigapascal. So the load found in column A, allowable load found in column A is applied on the column with an eccentricity 20 mm. 20 mm from the geometrical axis it's applied. So in that case, what is the maximum normal stress induced? Young's modulus is given as 204 gigapascal. So this case you have to apply the secant formula and find out the normal stress, maximum normal stress induced in the column. Now let us work out. Moment of inertia of the column cross section I is equal to bhq by 12. For a rectangular cross section it's bhq by 12. In this case we have a square cross section, so B and H are same, 100 mm. So 100 into 100 cube by 12, or 8.333 into 10 raised to 6 mm to the power of 4. That is the moment of inertia of the column cross section. And column cross section with respect to x axis or y axis, it has got the same moment of inertia. So there is no question of least moment of inertia here. Effective length of the column is 2L, because one end is fixed and the other end is free. So you can take the effective length as 2L, or 2 into 2.5 meter, or 5 meter, or 5000 mm. Euler's formula when load applied is along the axis, or load is applied centrally, P is equal to pi square EI by L square. Pi square into Young's modulus is 204 into 10 raised to 3, 204 gigapascal, so 204 into 10 raised to 3 Newton per mm square. I you have already calculated, 8.333 into 10 raised to 6, and L is effective length 5000. So substituting that, you will get the load as 6,71,106.25 Newton, or 671.106 kilonewton. So this is the buckling load when the load is applied centrally. So much load is required for the column to buckle when it is applied along the geometrical axis. Now allowable load you can find out by dividing this with the factor of safety. So allowable load that can be applied is that divided by factor of safety, or you get it as 335.55 kilonewton. So the load that can be applied on the column safely, that can be applied on the column, is 335.55 kilonewton. Now when that load is applied, the normal stress induced is that load divided by area of cross section, and we know that area of cross section is 100 into 100, or 10 raised to 4 mm square. So dividing this with the area of cross section, this is 10 raised to 4 and we have 10 raised to 3, so that 10 raised to 3 cancels here, you get 10. 335.55 divided by 10, or you get 33.56 Newton per mm square. So this is a maximum normal stress induced in the column when this safe load is applied. Now to solve second part of the question, first let us find out the radius of gyration. It's the least radius of gyration, but in this case I is same in both the directions. So you can find out k as root of I by a. I we have calculated as 8.333 into 10 raised to 6, and area of cross section is 10 raised to 4. That is 100 into 100, 10 raised to 4. So which will give the least radius of gyration as 28.867 mm. Now maximum normal stress induced due to eccentric loading, sigma max is equal to P by A into 1 plus EC by K square into C pi by 2 the root of P by PE. In this case, since we have already calculated the Euler's buckling load, it is easy to use this form of a secant formula. And also we know the load applied is half of Euler's buckling load. We are applying the load. After finding out the Euler's buckling load, now the load applied on the column is allowable load. Allowable load is calculated. Allowable load is PE by 2, and that allowable load is applied at a distance 20 mm from the geometrical axis. P is, in this case, P is equal to PE by 2. So P is PE by 2, and you will get PE by 2 by P, or you will get 1 by 2 or 0.5 under the root. So P by P is 0.5, and rest of the things you can apply. The load is 335.55 into 10 raised to 3. See, 335.55 kilonewton. So into 10 raised to 3 newton. Area is 10 raised to 4. Eccentricity is 20. C is the maximum distance to the outermost fiber in the direction of buckling. So that is 50 mm. That is substituted. And K is least radius of gyration, 28.867 into sec pi by 2 into root of 0.5. So which will give the maximum normal stress as 73.829 Newton per mm square. Now you can see that maximum normal stress induced in the column is more than double that induced when it is loaded centrally. So this is how you find out the maximum normal stress using secant formula for eccentric loading. If you have to use a secant formula to find out the load, maximum load that can be applied by substituting sigma max, maximum stress that material can withstand, that is yield stress, maximum yield stress that material can withstand, you have to solve this by trial and error. That's all for today. Thank you for watching.